Hi again, Professor Bob Young here, and we are going to wrap up graphing rational functions in this video. Now, in the previous videos, we've talked about graphs of rational functions that had horizontal asymptotes at y equals 0 when the top degree was smaller than the bottom. We've talked about the horizontal asymptote at other places depending on if, let's say that the degrees were equal in the top and bottom on x, then those coefficients in front dictated the horizontal asymptote. Now notice in this example, the top degree is exactly one more than the bottom degree. And whenever this happens, when that top power or degree is exactly one more than the bottom, there is no horizontal asymptote or ha, but there is what's called the oblique, or what Young likes to call the slant asymptote, which he abbreviates the SA. Now remember, you can divide the bottom into the top using long division or synthetic division, and if you do that, in this case, you're going to get the slant asymptote as y equals x plus 2. All right? And again, we want to look at those points around the vertical asymptote when we graph this thing, and we want to do some other things we've talked about in the last video. Now, to get the y-intercept here, it's going to be -1/2. Okay, now how do you get the y-intercept? We let x equal 0, so when we let that go to 0 and that go to 0, there it is, so we're going to say 0, -1/2. The graph has no x-intercepts. Now, why is that? Well, if you tried the other end of the coin here, what will make this numerator equal to 0? Let's try that over here. So remember, in order to get the x-intercepts, you've got to say what makes that numerator of a fraction equal to 0. And notice here, when we go subtracting 1 from both sides, we're going to have something squared equals a negative. So we could get some complex solutions, but no real zeros in this one. So we're going to just go ahead and say no real zeros. The graph does not intersect its oblique asymptote. Okay? Because if we take this x squared plus 1 over x minus 2, the function, and set it equal to the SA, the slant asymptote here, it will have no solution. Okay? Now, if you want to check that out, you may do so, but let's just go ahead and assume that so we can save some time watching videos here and get on the homework. So using the y-intercepts and some certain points here and the general behavior of the graph, what's going to lead us to this. So again, notice that I saw that the va was x equals 2, so I've got that. So I went ahead and I took some points, and I've got the SA here. The slant asymptote is y equals x plus 2. So if I were to graph this, I would start at 2, and I would use the slope of 1 over 1. So I would rise 1, run 1. I could even rise 4, run 4, the way this graph is labeled here, because notice I've had to extend x and y out a little bit to see everything real good. All right, so we've got those two lines plotted. I took some points to the left and the right of the va. So here's some points to the left of x equals 2. Here's some points to the right of x equals 2. And of course, we see that we have our y-intercept here at 0, -1/2. And there is what the graph looks like. So if we were to plot these points here as we are, that would be what the slant asymptote graph looks like. And it also looks kind of like the hook and the hugs, if you want to say that. All right, now, as mentioned earlier, a rational function must be defined by an expression in lowest terms. So in other words, this fraction must always be reduced to lowest terms. And in this last example, it was, all right? So we want to look at one last example here. A rational function that is not in lowest terms usually has a hole or point of discontinuity in its graph. So we're going to look at this last example here, and this is the famous line with a hole in it. So notice this fraction here, y equals x squared minus 4 over x minus 2. The top does factor in the difference of two perfect squares, x plus 2 times x minus 2 over the x minus 2. So those x minus 2's will cancel, leaving us with y equals x plus 2. Now remember, x cannot equal 2 because that would make that fraction what? Undefined. All right, so here's what we end up with, the famous line with a hole. So the graph of this function will be the same as the graph of this line, y equals x plus 2, with the exception of that point, that x value point with a 2 here. So notice, you know, some students even go, Young, why didn't you put a va down here? Well, maybe you could have if you wanted to, but see, since this fraction reduced into a line, this line y equals x plus 2, all we have to worry about is this hole right there, or point of discontinuity. So I think we have looked at just about every possible type of rational function we can now. So I'm going to turn it over and let you go and take care of that homework, practice, test, and let's get ready to rock and roll on some graphing. Professor Bob Young signing off.